So let's go ahead and get started. So it's my great pleasure to introduce today's speaker, Dr. Amy Furniss, who received her master's and PhD in physics at UC Santa Cruz, working on the Veritas collaboration, which is a collaboration to understand very high energy gamma ray emissions from extreme galaxy known as blazars. Right? After the completion of her PhD, Amy continued her research at Stanford University as a postdoctoral researcher for 2 years, before accepting a permanent position as a faculty member at CSU East Bay in Hayward, California. In addition to being a mom of 2 boys, she spends time outside teaching to coordinate observations of extreme gamma ray galaxies with space and ground-based telescopes. She's also involved in the highly successful CalBridge program, a mentorship program which supports underrepresented groups in earning their PhD in physics and astronomy in the UCs after completing their undergraduate degrees within the California State University system. She's also connected with Campere, and after the talk, again, not to impose on you, Amy, but she's willing to talk to you about any of those programs. They're fantastic programs. So please take this opportunity to talk to Amy afterwards about any of these opportunities, okay? And without further ado, Amy, welcome.
So I'm going to wear my mask, and you guys aren't going to understand anything that I'm saying.
No, you leave it off. We'll be good. Take it off, baby. You're all right. You're all right.
I understand you perfectly well, though.
I'm good.
I can hear you. I can hear you fine.
Can you do a show of hands? Fine.
This is peer pressure. No, that's peer pressure. So we're just going to follow the rules, people.
Okay, all right.
I'm going to follow the rules. They're set by CDC for a reason. All right, so I'm here to talk to you about the energetic photon, which I will speak about as though it has feelings and makes choices in life. But really, its life is a superposition of many different possibilities. You're going to figure out what those possibilities are today. Although you already got, oh gosh, I can't breathe. I haven't lectured in the COVID era yet because I'm on sabbatical, so I'll just lecture the whole time like this. It's all in my head. Okay, so this is who I am professionally speaking, as you already heard. So I went to Humboldt State, which is a California State University, just like Fresno State, it's just up north. While I was there, I did some undergraduate research down at Arecibo. It's no longer working, very sad. Now I work on building gamma ray telescopes. These are the gamma ray telescopes that I use currently, and this is the one that I'm currently trying to make work unsuccessfully, but that's 99% of a physicist's life. But this is actually who I am as a real person, so I don't identify solely as a physicist. I much more identify as a mother and somebody who is dedicated to helping the underserved populations access STEM education. So before we were forced to live in the COVID era and do all of our education online, I was already using the computer in order to make physics accessible to those who can't come to the classroom or may not have the means to get the preparation that allow them into the classroom at the college level. So I'm happy to answer any questions about this stuff. Oh, and I live in Santa Cruz, so it's very nice there. Not
Who's that group of people there, Amy? Who's that group of people? The group of people.
This is coverage. Those are coverage scholars. So, oh, and that one's Aaron, and that one's James.
There we go.
Yeah, the most important, best work of my life. Did a lot of publications, but who cares about that? All right, so the way this talk works is I've made it with active buttons, so that it's not just a serial slide. It's a slide that has actual directions that you get to decide what direction you go in. So instead of just clicking forward, I click on the slide. So how does a physics choose your own adventure story work? Well, has anybody ever read a choose your own adventure story? They used to be a lot more popular when kids used to read books. No? No? So I've read one of these books to my children, and it's what inspired me to come up with this talk. It's one of these things that you go to a junction and you get to decide. It's kind of like Dungeons and Dragons or something. I've never played that, but I hear that's what it's like. So now you guys get to make the decision, and we'll follow the decision that you make and figure out what happens to the photon. So you're going to have to vote. So at any point, do you tune out? It's okay. You'll start a new story, and you can tune back in. Because I don't know about you, when I'm listening to physics talks, I tend to tune out. Okay. So let's meet our photon. Our photon is a gamma ray. So this is what a gamma ray looks like. They travel light. Sorry, you guys are going to remember more humor than physics, but the secret is that there's physics in that humor, and so I taught you something. It's all a secret plan of mine. So photons come in different energies, and you've you've heard radio waves, you know very well this visible band right here. If you break an arm or you go to the dentist, they flash you with x-rays. Those are all photons. They're just different energy photons. If you take blue light or optical light and you go down in energy, wavelengths get very, very large, around the size of these, so microwave oven the size of these things. And then you have the gamma rays. Here, if you go up in energy, and I'm actually interested in photons that are off this plot. So I'm interested in gamma rays that are so energetic that you don't find them on Earth. So you could naturally ask, why do I have a telescope on Earth that looks for gamma rays that aren't on Earth? It's a fair question. Yeah?
How do you know there's gamma rays with higher energy?
Because I've seen them.
Okay.
I'll tell you later. And I theorized about them. By me, I mean physicists generally. Okay, so before we get to make any decisions of our photon, we get to learn the origin story. Every superhero has an origin story, right? Marvel Comics. I'm pretty sure Marvel Comics is going to pick this up next. The next movie. So this is our little baby gamma ray. Decided it's a he. Gamma rays, photons. It's not a boy, girl. Anyways, this is a little photon, and this right here is where our gamma ray is born. This is a supermassive black hole at the center of a gamma ray emitting galaxy. It's at the center of a very special type of gamma ray emitting galaxy. It is referred to as a blazar. So if you've seen pictures of galaxies, you may have seen some of these galaxies that have huge jets that are coming perpendicularly out from an accretion disk. If you take the jet and you actually point it right at us, the observer, like we're looking down the barrel of a gun, that's what a blazar is. And that's the type of source that emits gamma rays. So the type of source that is a special high-energy galaxy with a supermassive black hole right here at the center. The challenging part about this study is that we know that our gamma ray photon was born in this galaxy, but we don't have any idea where in the galaxy the photon was born. We'll talk about how they were born specifically in a moment. Some of you may have seen this picture. It's now the most famous black hole in all of the universe. Well, unless you count Interstellar's. What's this Interstellar's black hole name? Gargantua or something? Yeah. Well, this one's real, so it's even better. First Facebook page of gamma ray galaxies. This is M87, and this is the accretion disk, and there's the black hole. That's about the size of our solar system. And inside that size, there is 1 billion solar masses. So take the mass of a sun, multiply that by 1 billion, and then stuff that into the size of our own solar system. You come up with a black hole. That's what it looks like. This is actually images of the exact same galaxy. This image right here is taken way, 1,000 times smaller scale than that. And this is radio images, optical images, and X-ray images, and you can notice there's a jet. Observational evidence, done. Number one, there's a jet. So we have the radio observations show bright spots. Here's a bright spot, here's a bright spot. Optical observations, bright spot, bright spot. And you have X-ray observations, bright spot, bright spot. So this guy could have been born in any one of those bright spots, and we're just not sure. Notice there's no gamma ray observations up here. And I've been saying I'm going to talk about gamma rays, but there's no gamma ray image up here. Gamma ray instruments are not sensitive in the scale that these objects are. So if you were to take a gamma ray instrument and look at this, you would be able to see this part of the sky, so it would look like a point source. You wouldn't be able to disentangle this part from that part. So if you look with a gamma ray telescope, you just know it's coming from the galaxy. You don't know where in the galaxy it's coming from. All right, so to how it was born, not where it was born. It was born in a special relativistic way. All right, so the images that I'm going to show from this point forward are artistic renditions of these black hole accretion disk jet systems. So here's your first artistic rendition. You have your black hole. It's spinning because angular momentum is conserved even all the way to the depths of the black hole. So the accretion disk, very, very in toward the center of these galaxies. And then you have these jets that are emerging. And in these jets, if you go back, there's these weird little blobs of material. If you watch these blobs of material or of light, you'll notice that they move over many, many years because they're very large objects. What we think that those blobs are a blob. So here's an accretion disk right here, and it's a blob of electrons and positrons. The electrons and positrons are special because they're moving close to the speed of light inside the blob. So they're bumping around in here, moving almost speed of light, let's say 0.99 c. And then on top of that fact, we have this blob itself, which is somewhere in this jet, is moving down the jet at close to the speed of light, directly at us. Good thing that they're really far away, but it is moving directly at us. So you have this blob of relativistic particles moving relativistically. They don't move faster than the speed of light. And it's moving down in the presence of these magnetic field lines. Magnetic field lines also don't just miraculously go away. So if you had material that had magnetic field lines without magnetic reconnection, those magnetic field lines will spin up. They are embedded into the material within this accretion disk, and they'll be wound up. So you have one of these things moving in the presence of a magnetic field. So who can tell me what happens to charged particles in the presence of a magnetic field? Are you saying I'm crazy? Is it a party? They spiral. So, if we have a charged particle, magnetic field lines, it spirals. If it's spiraling, it's going around in a circle. If it's going around in a circle, it's accelerating. Centripetal acceleration, freshman 101 physics. I don't know if that's the class number. Is it 101?
4A.
4A. What? That's so confusing. Okay. So, fine. You have charged particles because of magnetic field. They're going around in a circle. As you have them going around in a circle, they will emit photons. Any charged particles that are accelerating emit photons. Particle physics 101, which you don't get until graduate school. Right. So you have photons that are emitted from this, and we see this here on Earth. We know this to be true. What kind of phenomenon shows this on Earth? Has anybody ever been up north, down south?
The lights.
Lights.
Yeah.
So what you're seeing here is the sun is constantly trying to kill us in many ways. But it's trying to kill us in this particular way by shooting charged particles at us. So those charged particles actually get trapped and spiral down the magnetic field lines that our Earth luckily has. And so with that, you get the charged particles spiraling and producing light, and that light happens to be in the optical band where we as humans get to appreciate it. So we know this to occur. The thing about it is, that if you have very energetic particles, you have higher energy light that's emitted. So for our magnetic field, that's not that strong, and the charged particles that the sun sends at us, we get blue, green kind of light that is emitted into our atmosphere. Let's take those charged particles and get them moving really, really fast. In a very, very strong magnetic field, we're not going to emit nice little friendly optical photons. We're going to emit big, mean, scary X-ray photons. So these X-ray photons are going to be emitted, and they're going to hang out in the blob of which they were emitted within. So now the blob looks really confusing because I've added photons to it. So you have your positrons, your electrons, and your little X-ray photons. These X-ray photons are not our main character. They are not gamma rays. X-ray photons, they're boring. They're down here. Meh. We want photons up here. How are we going to make photons up there? Well, we could turn the magnetic field way up, or we can make this thing move a lot faster, or we can ask a particle physicist to help us. So, The great thing about physics, if entropy didn't exist, is that things can happen in either direction. Physics actually doesn't say, except entropy, that things have to happen in a certain direction, and this is particularly true with particle physics. If you have a process that happens in one direction, you can reverse the clock, and it will happen in the other direction as well. So Compton scattering, which you learn about in modern physics, which I think there's a few students that are taking modern physics right now, Compton scattering says you have a photon that comes in, and it interacts with an electron, and you have the photon gives up its energy to that electron. So you have this poor little low energy tired electron, and it steals the energy from this photon. So let's say this is a blue light photon, now it's an infrared photon. And this electron is like super happy because it just got some free energy. It happens in reverse, it's called inverse Compton scattering. So now you have really energetic electrons. Where would we find those? Inside that blob. And we have photons that they created because they were in the presence of a magnetic field. So you have those X-ray photons hit the energetic electrons that made them and rob them of their energy. So you have an X-ray photon, steal energy, now it's a gamma ray photon. So you have to use these two processes, your synchrotron emission, that's the magnetic field creating X-rays, and inverse Compton emission to bump our X-rays up to gamma ray energies, and that is what creates our baby photon, which is the gamma ray photon. Does anybody have any questions? Yes?
In that blob with the electrons, and, where do they come from? Why do you have positrons and electrons in the blob in the first place? Or is that beyond everything?
It is not beyond the scope of this talk. It's just beyond the scope of our knowledge.
Oh,
no big
really?
deal. Yeah, no, that was what I tried to figure out as a graduate student and failed. If you know the answer to that, call me and we can talk.
I'm asking that.
Yeah, no, it's a great question. So we are trying to remain agnostic of the fact that there are relativistic electrons and positrons there, because I don't know how they got there. There's a lot of theory, but we don't know the answer yet. Okay. So now we have our photon, where it's time to move out. Has anybody ever felt like it's time to move away from home? I feel like that every morning. No? Come on, that's the funniest thing. Maybe I'm the parents of this. Yeah. All right, so this is another artistic representation. Here's the black hole at the center. They have a cutaway so that you can see in through this dusty torus. This dusty torus is all of the material that gets close enough that it's tidally disrupted. So if you had a star that's like, stars don't do that. But if you had a star that was coming toward this area, it would be tidally disrupted, broken up, and it would contribute to this dusty torus. So you have the jet, you have narrow-line region, you have a broadline region, you have the accretion disk, which is that little donut-looking thing, in case any of you want some donuts. So we're going to move out. And where we have to move out from is right there. Even if we're created somewhere in the jet, we have to move out from the very inner regions of this galaxy. So we have three options. We can move out and go hang out with Photon in the same neighborhood. Or we can explore the Broadline region, so that's this region, on our way out of town. Or we can just bust out of the galaxy and not interact with any of the stuff there. Which would we like to do?
So now we choose, huh?
Now you choose.
Do we vote or how do we do it?
Sure, let's vote. Who wants to hang out with the Photon in the same neighborhood? 2 people, 2 friendly people. Everybody else? Who wants to explore the Broadline region? 4 people, 5 people. I don't think I'm counting half votes here. Who wants to just bust out of the galaxy? Oh, come on, anti-social physicists.
There you go. They're the winner.
You know what? We're going to explore the Broadline region. I think you all need a little social exposure here. Even though it's time to COVID, everybody just wants to get out of the galaxy so they can take their mask off.
Just like real life.
Just like real life. There's no
Never get
COVID.
what I want.
All right, so another artistic representation of the galaxy. First, I'm going to tell you what a broadline region is. See, I'm secretly trying to teach you physics. Sorry. All right, so this is way down into the depths of this gamma-ray emitting galaxy. So here you have the black hole, the accretion disk. The broadline region is this little area of like It's a cloud of material, of like, I don't know, hydrogen and helium and a whole bunch of, material, stuff, mass. Then you have this dense torus out here, and we're looking at these blazars from this perspective. If you look at a different type of galaxy from a different perspective, or the same galaxy, I should say, from a different perspective, it looks totally different. So you can see that there's a challenge here that we have to only study. We get to study more than just blazars, but we only get to look at blazars from this direction. So the Broadline region, why do they call it the Broadline region? First, let's note there's the narrow line region is the gas out here. The Broadline region is the gas in there. It's the same gas. So why is one called narrow and one called broad? Well, Doppler shift. So you have a central mass and you have material moving around it. The closer you get to that central mass, the faster it's going to move. And from your perspective, what you're looking at is you get to see the material going toward you and away from you, and toward you and away from you. So if it was stationary, you would see the material as a perfect, well, I mean, there's some quantum broadening and all of that kind of stuff, but you would see narrow lines if the material was stationary. But the material is not stationary. It's moving around the black hole, and so it's broadened. The stuff closer to the black hole moves faster and is farther broadened than the stuff farther away from the black hole, which remains narrow. So to go back, this gas moves really fast because it's close to the black hole. This gas doesn't move really fast, so it's narrow line. Broadened line, narrow line. So now that you know what the Broadline region is, what kind of interaction are you going to have? There's a lot of potential interactions. These are the boring kind of interactions that you learn about in undergraduate physics. And then if you turn the energy up, well, modern physics, you'll learn about Photoelectric Effect. You hit that electron and it goes away, or is dissociated. But if you turn the energy way up, you have a photon that comes near in the vicinity of an atom, and that photon turns into an electron and a positron pair. Has anybody ever heard of that equation, E equals mc squared? This is that equation, like in real life. I think you PhD saves, J saved I, R, L. No? Yeah. No, you're not that young. That's how IRL. Okay, so pair production, if you go to really high energy, pair production is actually the dominant interaction. So a photon gets close to any material in the Broadline region. Our photon is really high energy. He's a gamma ray. He's going to produce an electron and a positron, which unfortunately means he's no longer a photon. He died. Game over. So we're going to have to go back.
I knew that was bad.
Yeah, well, I mean, I had that. So we're going to go back. We're going to do either one of these options. I can tell you just as a hint, if this gamma ray gets close to any material, may it be our atmosphere, may it be another photon, may it be anything like that, it's going to interact. So let's just bust out of the galaxy, try to live as long as possible, keep our heads down. We're going to make it through this, okay? All right, so we're going to bust out of the galaxy. Okay. A bit artistic rendition. So here's our gamma ray, and he's leaving the galaxy, dusty torus. Narrow line region is way up here, heading toward Earth. This photon has to travel from a galaxy to get to us. It has to travel for a really, really, really long time. Like, if you thought your commute to work was bad, I'm going to put it in perspective for you. So many of these objects that we look at that are gamma ray emitting galaxies are at a redshift of 1, which if you're not an astronomer, redshift means nothing, especially if I tell you a redshift of 1. It could be a redshift of 492. It doesn't matter. But what it is it's a measure, using the Doppler shift, it's a measure of how far these galaxies are away from us. So you may or may not know that our universe expansion is accelerating. So the farther away from us you are, the faster away you're moving. So the Doppler shift increases for objects that are far away. So the redshift increases for objects that are far away. So redshift of 1, what does that mean? It means that this galaxy is so far away that when it was emitted, the universe was only 8 billion years old. That's how far away it is. 8 billion light years away. That's a distance. The universe was approximately 8 billion, 7 billion light years old. The universe has been around, estimated, plus or minus, for 14 billion years. So a photon emitted that's from an object that far away has to travel for 8 billion years to get to us. It takes, in the time the photon travels, about 8 billion years, the universe has expanded another 2 billion light years. So it's been so long that now the poor gamma ray, once it gets to Earth, the gamma ray came from a galaxy that is 10 billion light years away. So it's coming a really long, long way. And the important part of that is that, do you want to do this trip, this really long distance trip, do you want to just keep to yourself? Sing some songs, play some card games, I don't know. Or do you want to find a cool low energy friend, I don't know, like a low energy photon to hang out with on your way from the galaxy to us? Vote for friend or loner? Friend. Now, once again, let me reiterate that all of these things, all of these potential pathways that I'm talking to you about, they all happen. So one photon is emitted, and it has the potential to go through all of these. But if you have 100 photons emitted, some of them will make it all the way to Earth, some of them will be eaten in the Broadline region, and some of them will be eaten along the way when they hang out with cool, new low energy friends. That guy. Has anybody ever met that guy before? I see him find that guy all the time. The cool guy. The cool low energy guy. How's this photon? How was he born? I don't know why. I don't know why I give gender to my photons, but whatever. Well, the universe has been around for a while, and we have some crazy, in the beginning, there was some unexplained inflation, because it answers a lot of questions that we don't understand about the universe. So don't ask me about that. Ask a cosmologist.
Can you develop it?
What?
Never mind, I was going to make a joke.
A cosmologist.
I was going to say, like any major development, there's always overruns, isn't there?
Oh, yes, yes. So here you have the Dark Ages. Again, we don't understand the Dark Ages. We had those in human history as well. But then there was the stars that started to form. These stars started to form in galaxies. And what do stars do? They burn. And they create photons. What kind of photons does our sun create? Should be optical. I was going to say, we can all go outside and look at the sun if you want. It creates optical. That's why we have eyes that are sensitive to visible light. Because the majority of the sun puts out light in the optical band. Yellow, green, blue. Our sun isn't that special. It's like every other star of its kind of size. So you have, since the beginning of the universe-ish, plus or minus a billion years, you have these stars that are producing photons, and those photons don't go anywhere. They just hang out. Hey, they're just hanging out in the galaxy, waiting to interact with somebody or something. So that's where this guy came from. He's an optical light photon. He could have been produced by a star back here. He could have been produced by a star here. He could have been produced by a star here. So he's hanging around, and there's a whole bunch of other photons. Ooh, big scientific plot here. So what you're looking at, I'm just going to explain the axes first. Here you're looking about the wavelength of the light. So this is higher energy. If you're an astronomer, you're feeling happy because energy decreases to the right on that. So this is low energy photons. This is infrared. This is optical. And this is the relative intensity. This is a measure of how many photons there are in the universe that are optical photons. So there's a lot of optical photons. There's fewer UV photons because stars don't put out very much UV light. Then you have this weird trough thing, and then you have this onset of infrared radiation. That infrared radiation comes from the fact that starlight is absorbed by matter and then re-emitted. And when it's re-emitted at a lower energy, infrared. So things that heat up, they emit that heat. So our kind of, this is all theoretical work with the data points that nobody can measure this because it's the light that is in the universe. How do you measure the light that's in the universe when you're sitting right next to a really bright star? I don't know. This is where our photon is. He's at a special energy so that when you meet up in deep, deep space, this guy, boom, some magic particle physics happens. And that magic particle physics says that if you're the right energy, you produce an electron and positron. The electron and positron pair production is super common and is kind of the demise of our gamma ray photon, no matter what. No matter what, the gamma ray photon will turn into an electron positron pair. Spoiler alert. But it has to be, this photon has to interact with the photon that if you add the energies up, you get at least the rest mass of 2 electrons. So it's E equals mc squared, where it's actually 2 mass of an electron squared. C squared. So that you have, and if you have any excess energy, these electrons and positrons will have that kinetic energy and they'll keep going forward. So if they were exactly the same energy, if you add 1 TeV to 1 EV, and it was exactly the energy of an electron and positron, they would just be produced and they would be stationary. They would have no excess energy. But you have excess energy and they're still being kind of in that same direction. So this could be the end of the story, but it's not, because I love listening to myself talk. No, this isn't the end of the story, because if it was, I wouldn't have a job. Many people would not have a job. They'd be like, well, that gamma ray photon was produced, but we could never observe it. So was it really produced? We don't know. Luckily, particle physics in the universe allow very clever techniques in order to study the universe around us. So this is the picture so far of what's happening. Here we are sitting on Earth trying to finish our homework. And here's a gamma ray galaxy emitting gamma rays. That's the blue arrow. Here's a normal, boring old galaxy that just emits boring old optical light. So that's where you get your photon, that's your cool photon, your low energy optical photon. They interact and you get an electron and positron pair. Boom, do they sit there in space? Well, it depends where they're produced. So we're going to have to decide where in deep space they're produced, because deep space is not actually just a big vacuum, like Star Wars Trek, one of those shows, would tell you about. It's not really just a big vacuum. There's a lot going on. You may have seen this kind of simulation, or maybe you haven't. It looks like a spiderweb, or a nice marble, maybe an Italian marble you'd put in your kitchen. So it's a simulation of galactic formation taking into account dark matter. I'm not going to touch on dark matter. Some cool stuff, not my field of expertise. You're going to notice that there's bright areas and they're kind of clumpy. There's these filaments, these lines that are attaching, going from one dark area or bright area to another bright area. And then there's these dark areas. So what that is, these are clusters of super clusters of galaxies. So it's not just, this is not just one galaxy. That is a cluster of at least 1,000 galaxies. So you've got hundreds of thousands of galaxies right here. Each one of those filaments has galaxies in it. Each galaxy has 100 to 200 billion stars. So this scale is ridiculous. But we could say the gamma ray is emitted from a place in one of these galaxies that make up this cluster. And maybe we are in a Milky Way galaxy that is in this cluster. This is simulation, it doesn't exist, it's not real data. Our gamma ray has to make it through this kind of like web that is the cosmic web. So if it's produced and then or interacts with one of those low energy photons right here, I'll do it better. If it interacts with something in one of these bright regions, It's going to be interacting around a lot of galaxies. Or it could interact in one of these voids. These voids are actually the largest structure in the universe. And that's based strictly on how old the universe is. As the universe ages, these voids will just become bigger and bigger and bigger because gravity pulls. I would say gravity sucks, but it doesn't. That's a misnomer. So, where do we want our interaction to happen? Do we want it to happen where there's a large magnetic field? What creates a magnetic field? Moving charges. Moving charges exist in galaxies. So, do we want it to interact with our low energy photon here? Or do we want it to interact with our low energy photon there? Who wants large magnetic field? Large magnetic field means around stuff, okay? Who wants it to interact, or a small magnetic field in a void? Okay, so that was totally split. I'll go with this option here. All right, so, just like real life teaching. What do we mean by high magnetic field is the first question. If I was to ask anybody in this classroom, what's the magnetic field of the Earth?
3.
3 pi.
-4.
Square root of 3 pi over 2.
10 to the -4. Tesla.
Okay, I didn't know the answer to that. You get A. You get A. All right. So the point being that we don't really have a measure of what a good what's a magnetic field? What's a normal magnetic field? Why are we on Earth setting that norm? I don't know. Magnetars. The bigger an object is, the smaller its magnetic field. So the smaller an object is, a neutron star, which is an entire star smashed into a 10-kilometer diameter object. It has a really high magnetic field, ridiculously high magnetic field. Again, not my field of expertise. Cool objects though. Earth, it's bigger, small magnetic field. Milky Way, much bigger, even smaller magnetic field. So, where is the magnetic field going to be the largest? Well, it's going to be the largest around those dense pockets of baryonic material, which is galaxies. That's where all the baryonic matter is. So, this is what happens for a high magnetic field. Again, synchrotron radiation coming back at you. Here's our gamma ray photons, the blue photons coming from the blazar. Here's the low energy photon that is going to interact with our high energy gamma ray photon. They produce an electron and a positron pair in the presence of a large magnetic field. What does a magnetic field do to charged particles? Yeah, it deflects them, it makes them spin. So they get deflected a lot off of their line of sight. So we'll never see them again because they have the ability to get their energy back. So you have this interaction, a optical light photon comes in, it's deflected, but you also have other photons hanging around that they can steal that energy. The photons can steal the electron's energy. And then they're gamma ray again. But the gamma ray is not going to go toward Earth because it's been deflected. So now let's think about, can we observe that gamma ray? No, it's not coming anywhere near Earth. So, game's over. But, if we were to have made the correct decision, no pressure. If this stuff happened in a void, so in one of these pocket spiderwebby things, no baryonic matter moving around, no magnetic field, so you have your electrons and your positrons that are created, they're not deflected. They just keep on trucking forward toward their original line of sight. So, these are going towards Earth, the electron, the positron, it's dramaticized here because I've drawn them. They're also going towards Earth. So you have one, it interacts with the EBL, it steals, this photon steals the electron's energy and is changed back into a gamma ray. So even though it's not the same gamma ray, it's still a gamma ray moving toward Earth from the direction of the galaxy. So we can still detect this gamma ray. Luckily, NASA's around, and as that gamma ray goes toward Earth, hopefully it's happening at the same time, that the Fermi Large Area Telescope is passing around its orbit. It's orbiting around Earth. It's orbiting around Earth here. So the gamma ray is going to hit this detector, this telescope. This telescope doesn't look like any telescope you've ever seen. It's actually a particle detector, one of the smallest particle detectors. So when you have a gamma ray, well, you see this is the telescope right here. This right here is just what powers the telescope, solar panels. Inside you have a whole bunch of silicon trackers. The same kind of silicon trackers that are used inside particle detectors that are based in Europe and in Chicago. So the gamma ray comes in. As the gamma ray comes in, it hits one of these conversion foils, and what does it turn into? There's a trend. It changes into an electron and a positron. So in the end, these gamma rays are doomed. Anything goes near them, they turn into an electron. They get scared, they turn into an electron or a positron. That's what happens. So then you have that electron and that positron, they deposit into a calorimeter. We can measure the energy of you add the energy up here, and you're like, okay, well, no energy is lost. So the summation of those two energies gives me the energy of the photon. And you can track them back in the tracker and be like, okay, so it came from that part of the sky. So, with that information, we can study this photon. So, what do humans want to know about photons? When you look up in the sky and you're an astronomer and you want to use these photons in order to study the universe, you need to know three things. First off, you want to know how much energy it had. That's like, was it a blue light photon? Was it an X-ray? Was it a gamma ray? That'll tell you something about the object that emitted it. You want to know where it came from, so you don't want to be like, did it come from over there, or down there? You shouldn't look for photons straight down. Just for future reference, that's not going to work. And when it arrived, because if this is something like two neutron stars merging and turning into a black hole, knowing exactly when those photons showed up allows you to know exactly when they were created, and then you can know exactly when this cataclysmic transient event happened within our universe. So, the other interesting thing about this is that this is now true. When I started my studies at UC Santa Cruz, we had photons to study. And that was it. So we had a whole bunch of astronomers running around and being like, look at this photon, look at this photon. I almost blinded you guys, sorry. But now we have gravitational waves, we have neutrinos, and all of these things are coming from the same sources out there in space. So it's like, at first we're able to see with our eyes, we watch something in space unfold with our eyes by looking at photons. Then all of a sudden, we're able to hear the event with gravitational waves, and we're able to smell the event with neutrinos. I don't know why neutrinos are smelly, but in my personal opinion, they are. So we have way, way more that we can learn when we actually look at this in the context of all these sources. So, what path we followed is we were born, and then we decided to get out of the galaxy, because if we play the Broadline Region, we die. And then we hang out with a cool new friend, and then we are detected by, in a small magnetic field, we're detected by the Fermi telescope. There's another path that allows you, if you don't interact with anybody, you want to stay solo, there's a direct path to fame. And I can go back to the direct path of fame if you guys want 5 more minutes.
That was that choice we didn't pick?
Yeah.
Okay.
Do you want 5 more minutes?
Yeah, I do.
Yeah.
I do.
Okay. All the students are like, please, please stop. Like every physics class I've ever taught. Okay. All right. So what we just did is we hung out with a cool new friend, which was possibly death, our demise. Or if we interacted with one of these cool no photons with no magnetic field around, we were cool. It's fine. Now we're just going to put our head down. We're going to study solo, and we're going to make it straight from the galaxy all the way to Earth. No interaction whatsoever. Nobody's turning this gamma ray into an electron and positron. Boom. So easy. If this was what real astrophysics was like, I also wouldn't have a job. So, you know, you want it to be kind of a complicated question, but not too simple, because then there's no more questions to ask about it. So you have a gamma ray photon, travels all the way to Earth, and it keeps all of its energy. So it's way, way, way energetic. Now, keep in mind, who remembers how long this photon has been traveling?
I know.
Like 8 billion years?
Yeah.
For a while, right? Like, it's really hopeful. It really wants to become famous. It really wants to get studied and show up in a Nature paper. So, it's coming, and luckily it's going to land right where there's a gamma ray telescope. Because if it landed right here, man, what a waste of life. It would be so frustrating. If it, you know, like, actually, we can complicate it even further. So you have this gamma ray photon coming in, and it's directed directly at one of the most sensitive gamma ray telescopes on Earth. Success! Except, you can't make it through the atmosphere. What happens to gamma rays? They turn into electrons and positons. So, funny thing that we tricked the National Science Foundation into putting a gamma ray telescope on the ground, and gamma rays don't even make it through the atmosphere. We are so smart. Actually, we are so smart because we don't look, and we are never able to detect the gamma ray photon itself. The only thing we can ever detect is the electron to positron pair. Because what happens when you have a gamma ray come in and hit the atmosphere, it's super energetic, remember? It's happening, its pair production is dominant. So you have an electron and positron pair. The electron and positron pair happen right here at the top of the galaxy, and then they move. They have so much energy. They move through the atmosphere faster than the speed of light. Does anybody have a problem with that?
Yeah, we were all silent when you said that. Huh?
Anybody have a
Faster than the
problem?
speed of light, huh?
The electron and the positron move through the atmosphere at faster than the speed of light. Did you guys all just lose respect for me? I have a PhD, thank you very much. They actually do. So there's a rule. Somebody might have heard the rule, don't move faster than the speed of light. Don't move faster than the speed of light moves in a vacuum. You cannot move faster than how fast light moves in a vacuum. But it slows down. Light slows down when it goes into a medium. When it goes in air, when it goes in water, when it goes through jello, it slows down. Just like you slow down if you're trying to run and then you run through a river, you're going to slow down. It's not exactly the same. Relatively complicated. Take an E&M course. Anyways, so the electron and the positron are moving through the atmosphere at close to the speed of light, c, 3.0 times 10 to the 8 meters per second. But light is only moving through the atmosphere at 90% of that. So, or 95% of that. What happens is particle physics kicks in and says, whoa, 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 whoa. And it creates this light. So you have, just like a sonic boom, when an airplane moves fast through our atmosphere, faster than the speed of sound, you get a sonic boom. When any object moves through a medium faster than the speed of light, there's a light boom, which is referred to as Cherenkov radiation. And Cherenkov radiation happens to be blue. Blue light is super easy to pick up with normal reflectors, like mirrors. So we can use normal reflectors, normal cheap reflectors, in order to reflect this blue light that has been produced from a gamma ray hitting the atmosphere in order to learn about that gamma ray that created that blue light in the first place. So, we've got our gamma ray. He's traveled for 8 billion years. He really needs to stretch his legs in the Hall of Fame. He's coming down, produces this perfectly on top of the telescope array. Amazing, nailed it, but the telescope operators were sleeping, so we didn't detect. Just kidding. So we have a lot of options that could go wrong here. The telescope operators could be sleeping, telescope hardware could be broken, there could be clouds in the sky, it could be a bright moon, the telescope could be off. Let's see, let's randomly pick one of those. Oh, game over, photon dies. Super frustrating, right? Traveled so far, didn't get to go in the Hall of Fame. So as long as everything's working, we can measure this photon, and the things that we want to measure from the photon allow us to put that photon into context. So this is a Veritas result, another emoji for anybody interested in how to lecture with emojis. I do a workshop on it. So this is a detection of a gamma ray that actually came from a galaxy that also emitted a neutrino at the same time. So the fact that you have a neutrino and a gamma ray coming from the same object tells you that there's some sort of hadronic process going on. Going back to the first question of how did that blob of particles even get there, that's how we'll answer that question, is that if we see that there's some correlation between neutrinos and photons, then we can actually say, oh, these are protons, these protons are created, they have this energy, and that's where they're coming from. So we have to use our telescope by matching it up with what other telescopes see. And, you know, if you wanted to read the paper, go ahead. Okay, so with this, the Veritas telescope does all the things. We know how much energy it has, we know where it came from, we know when it arrived, and but boom, it makes it to the Hall of Fame. Look at right there, right next to, I don't know who that is, or I don't know who that is, that person, don't know. But anyways, the point being, you're able to measure the photon. All right, so at that juncture, I have nothing else to say, and I appreciate your attention.
Okay, so we have time for some questions. Oh, we can turn the lights on. So that one guy's Ray Bradbury.
Yeah.
That is Ray Bradbury. Isn't
Yeah,
it?
I know it is. I know it is because, yeah.
Oh, okay, good.
I looked for a scientific Hall of Fame, but it didn't come out so well.
He's in the science fiction hall of fame.
Oh, well, good. Your telescope detected an episode of Cherenkov radiation coming from gamma rays falling from the heavens onto the atmosphere. How does that information lead back to the energy of the particle?
Yeah, great question. So, the more energetic the gamma ray is, the more electrons and positrons that will result in the air shower, and the more Cherenkov light will result. So you'll see a bigger, brighter shower, and you can actually relate that back to...
So just directly the intensity.
Right, and the only way we can study that is the calorimeter of our particle detector is the atmosphere. So we have to simulate the atmosphere, and you throw a gamma ray at it, and you say, okay, gamma ray of this energy creates this much light on a computer. So then you find out that much light, and you have to use that lookup table in order to say how much energy the original photon had.
I suppose there'd be a certain amount of interactions that maybe a star that's producing a lot of blue light at some particular time.
We're clever on, yes, so background, it's called night sky background. So it's starlight, and not only just the starlight, but the blue light from, so we're based down in Central Tucson. Tucson has a whole bunch of blue lights, and that blue light goes up into the atmosphere and reflects back down, and our telescope picks that up too. But we trigger on very rapid, non-constant sources of blue light. And when I say rapid, I mean 10 to 12 nanosecond flashes. So the background light's taken out.
So this light, this blue light, is it very kind of, I don't know what the right word, stochastic, or I mean it's like boom, 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 boom. It's not like, there's not enough of it hitting where it's like a constant flow.
So there's a constant background.
From these,
but not all of it are gamma ray initiated. So the constant background is actually, if you look at a gamma ray source, then most of them are going like a galaxy that emits gamma rays. You'll see a lot of them and be able to tell that they're gamma rays. But the sun and everywhere in our galaxy produces really energetic electrons and positrons. When electrons and positrons hit the atmosphere, they result in the same shower. So we do have this general background of showers that are produced, and then we have to separate that background of showers to gamma ray only, just based on where we expect sources to be.
But it's because it's hitting the atmosphere. So a space telescope wouldn't be any help to you if you're looking for this blue light. But as far as looking for these high energy photons, like this would more and better space telescopes be useful to?
So the thing that we use the space telescope for specifically is that, so I want everybody do this, since you all been sitting here for a while, everybody do this. And everybody do this. Just kidding, do this. Now move your arms out and stop when you can't see them. Just look forward and stop when you can't see them anymore. And if you're sitting really close to somebody, make sure to do it really fast. So the space-based telescope can see that much sky, as much as a human can see. If you do this, and actually just like one fingernail, that's as much as a ground-based telescope can see. So we use the space-based telescope in order to look at the whole sky, 1/3 of the sky, at once and say, there's a source, there's a source, there's a source. Then we point our telescope directly at that one point. And then we know it's a gamma ray source.
Actually, I had a question along those lines. You depicted the Cherenkov radiation cone as having a size that is almost on the order of the size of your array. Is that accurate? How big is the cone of light produced?
It is exactly accurate because that's why our array is that size. Yeah,
That's your design.
so we just followed nature in that, and that we know the energy of these gamma ray photons creates footprints or light cones on the ground that are this big, so we put telescopes at the edges of that cone.
And for the record, how big is that footprint?
They're about 100-meter sides of a tetragon.
Okay.
Yeah.
So the reason to have that on the setup of those satellites, because it's much easier to, I guess, read the blue light better than having the positron and electron, or directly measuring those instead.
So it's actually that they're mutually beneficial. So the telescope, the space telescope that's actually reading the electron and positron directly, it's only the size of half of this desk.
Okay.
So it's got a very, very small footprint, and because it's only that size, the more energetic gamma rays don't even pair produce in it, they just go right through it. So they're actually sensitive to lower energy gamma rays, which low energy gamma rays exist. Yeah, they're lower energy gamma rays. And those, the lower energy gamma rays, when they hit the atmosphere, they're so weak that they can't produce a shower. So Veritas would never be able to see them. The ground-based would never be able to see them. So what the space telescope sees, the ground-based telescope never had a chance. What the ground-based telescope sees, the space telescope never had a chance.
Okay.
Yeah. Again, the scientists are clever. I hope to be one someday.
More questions? Well, if not, let's thank Dr. Furniss again. And again, so Dr. Furniss had mentioned the programs that she's connected with that would be beneficial to you guys. And also, if you're at that point of maybe thinking about a PhD program, come down. She's also happy to talk to you about that. So thanks again. And we still have some donuts left. So
Thank you, everybody.